Next up, as we talk about Gauss's law, is our Gauss's law with cylinders. Right now, my computer is making a very annoying loud noise. Hopefully it's not showing up as you're listening to this, but if it is, please, that's my computer. It's not something that's going on at home. This is a really typical problem. What we're going to have is a long, thin wire, very long, of some length L, that is completely charged wire such as this. And it says it has linear charge density. You need to remember that linear charge density is lambda, which is charge per unit length. And so our task is to pick a Gaussian surface that's going to help us. Now, a sphere is not going to work because the electric field will not be perpendicular to all points on that sphere. And so the best shape that we can do is to use a cylinder. And so if I use a cylinder around this shaped object, hopefully that you can see is that every little point, my electric field, I can't draw that coming out at me, is going to be coming out perpendicular to the surface of this cylinder. Now, what about here on the ends? On the ends, I do not have to worry about because these endpoints are going to be parallel to that line of the path, so the only component or the only area in which a flux will be felt is this surface area of this cylinder. So I just have to worry about the surface area. I don't have to worry about these endpoints. And so now as we apply Gauss's law, and hopefully you remember Gauss's law by now is Q enclosed equals epsilon times my flux. And my flux, of course, is the integral of E dot dA. So what area am I going to be using here? Hopefully that you will see, well, you will see here in just a second, you need to use the surface area of that cylinder. And so that formula for that surface area of the cylinder is going to equal to 2 pi RL. And if you want to know where that comes from, the circumference, I'm going to break it open. And so that's going to be that length on one side, and then I'm going to multiply that by the length of my cylinder that I use. So what do I substitute for this Q enclosed? I go back up to my linear charge density, and so that Q enclosed is going to equal to lambda times L. So I'll have lambda times L equals epsilon times E times my area, which is 2 pi RL. Hopefully you can see that this length cancels. So it doesn't matter the length of the wire, doesn't matter the length of my Gaussian surface, because that L is going to cancel every single time. And so as I solve for that electric field, I get lambda over epsilon times 2 pi R, and R is going to be that radius from the point of which I'm trying to find the electric field to the center of my cylinder here. And that's it. That's all we have to do on that one. Of course, on the AP test, it's going to make it much harder because we'll have a coaxial cable, which will have 2 cylinders on the inside, and we'll have to do a whole lot harder on that. But this is our basics for what we need to do here. And so work through some internet problems, and we'll work through some free response problems and see how you do on this.